soon. So, trying to get something down. Yep, yep. We good. Thank you. Okay. So, we'll talk about this later. We're going to keep going with what we talked about on Monday. So, photoelectron spectroscopy. We kind of puzzled through what we expect to see. So we're going to get to now real data eventually, which we're going to use to come up with an extension to the shell model, an improvement. And then that's going to get us to electron configurations and actually a further explanation of the layout of the periodic table. So, photoelectron spectroscopy, again, this is different from the ionization energy data because ionization energy experiments will only remove the easiest to remove electron, the electron that has the lowest ionization energy. That's usually the valence electrons only. This new technique, though, photoelectron spectroscopy, can remove any of the electrons in an atom. The easy to remove ones on the outside and the really hard to remove ones on the inside. So we use the light, in this case X-ray photons. These have really high amounts of energy in them. And we can calculate, so we hit the atom with some of this high energy light. That's the equation for energy of a photon with the frequency. The electron comes out with a certain amount of kinetic energy. That's their energy of motion. And we can subtract that kinetic energy from the photon energy. What's left over is the energy required to remove that electron, the ionization energy. So this is all happening in the computer. The computer generates your spectrum, and it plots ionization energy of that electron or whatever that it detected on the x-axis. Again, this is a basic how it works. Here, I might as well show you the video. You guys didn't see it last time. So, photoelectron spectroscopy, also known as XPS, X-ray photoelectron spectroscopy.
Behind me is an XPS machine, or X-ray photoelectron spectroscopy machine.
Gigantic thing.
So we call it an X-ray machine because we use X-rays to probe matter. We probe this matter by shooting these X-rays out of this tube at whatever our sample is. And so the X-rays come out at a certain known energy and they knock off electrons. So we all know that the structure of matter is atoms, and these atoms are formed with a nucleus and electrons orbiting around it. These electrons orbit around the nucleus, and they're bound to it at a certain energy level. So these electrons, or the X-rays, come in and they knock off our electrons. So the electrons go shooting off in all directions, but we have a lot of electrons come shooting up this tube. So the electrons get curved around here by an electric field. Based on how much they curve, we can tell how fast they're going. And how fast they're going tells us their energy. And so their energy tells us how strongly they were bonded to that center nucleus. This bond energy can tell us a lot of information, including what that nucleus is. So by knowing what your nucleus is, you can know what your material is. And you can use it to tell if you have carbon in here, or sulfur, or lithium. You can tell almost any material. And you can also tell how it's bonded to its neighbors. As carbon bonds to another carbon atom, it shifts the electrons in its orbital, and that gives us a slightly different energy level. So I use that information to probe solar cells. P3HT PCBM solar cells have been around for the last 11 years, but they've been slowly coming up in efficiency and knowledge in general. They started out at less than 1%, and the newest solar cells today, not P3HT PCBM, but other organics, are over 8%. So that's a huge leap, and that leap is brought about by machines like this one. The unique thing about P3HT PCBM is it's an interface of two different polymers, one of which has sulfur atoms along with carbon and hydrogen, the other which only has carbon and hydrogen. So using this beam, we can tell if we have sulfur or if we have carbon and hydrogen. So this peak right here is due to sulfur, telling me that I'm looking right now at a P3HT polymer. I'm Roy Murray. I work for Professor Ismat Shah, and I'm at the University of Delaware.
So anyway, this is typically what a vacuum chamber looks like in a chem or physics lab. It's like this gigantic stainless steel chamber with all these ports that have flanges that are standard size. So they can be sealed off. You can attach other instruments to it. You can attach glass covers so you can see in. Yeah, and then at the bottom there's this gigantic vacuum generator. So first they start with a pump that, just like if you were doing AC, you're going to be doing AC in the car or home, you have to pump out the air. But that's not good enough vacuum for science labs. You have to, once you get the air out that way, you get it down to super low pressure. Then you have to use an oil pump. So like this, it generates a vacuum using oil. So the oil is sprayed in droplets downwards, and the oil droplets hit air molecules and force them down. It's weird how it works, but that's how we get to super, super low vacuums. High vacuums, I should say. Super low pressures. Anyway, yeah, you don't want anything else in there. You just want to analyze your whatever beam of molecules you're shooting in there. Beam of atoms. Anyway, that's what they look like. They're not super interesting looking. It's mostly just a giant metal thing with a computer attached. There is an X-ray laser somewhere.
Kind of his arm. His point guy.
Yeah, one of the side arms. Yeah. You don't want to be exposed to that either. So it's self-contained. All right. So we talked about this. The outer electrons have a lower ionization energy. The inner electrons have a much higher ionization energy. So there it is. Inner ones are larger ionization energies. But photoelectron spectroscopy can remove any one of these electrons. We're not stuck with just the outer shell, which is what the data we saw before was. The ionization energy is just the outer shell electrons. That's it. So we went through this. This is the sample, hit the atom with this much photon energy. An electron comes off with a certain kinetic energy that's related to its speed. If you take the difference between the two, that's the ionization energy. And that's what's plotted here. And again, remember that this height of this peak we can't, by itself, it doesn't tell us how many electrons. And that's because the way the experiment works is you're not just analyzing one atom, you're analyzing a stream of atoms. Each atom is getting hit by one photon, and an electron is coming out, but it could be from anywhere inside the atom. So it's not like you're taking a single atom, removing all the electrons and counting them. It's just, so there's no way to tell how many electrons came out. All you're seeing is a signal at that ionization energy. So we did this. Then we did this. So if you have an atom that has these 5 electrons at 2 different energy levels, what you can see is a ratio for peak height. And we should see a 3:2 ratio because of the number of electrons naturally arranged in the atom. And that's just going to come from probability. You're going to do this experiment in the machine. It's happening, I don't know how many thousands of times per second. And as you get all this information, it's going to average out to show you these numbers, these 3:2 ratios. So you'll get 2 peaks, one corresponding to this ionization energy, one corresponding to this ionization energy, and then in a ratio of 3:2. So we did that. So I think what we're left with is now starting with some real data. So let's say we have this unknown atom, and there's the simulated photoelectron spectrum. Simulated meaning we're showing you perfect looking data. You saw what his computer screen looked like. It was like a really broad, ugly looking peak. Lots of noise. We're making it easy on you. This is perfect. Unlike the lab today where you had all this light everywhere and you were like, how could one of these unknown lights or samples be that CO2 spectrum that had the very, it only had 3 peaks in the diagram, and none of them had just 3 things. So, real data is often harder to read. So, let's go through page 168 and just do questions 12 and 13. This is like a warm-up for some real data, so it's not too hard. Questions actually right there on the screen. Just in case. This is table 1 of Chem Activity 4, so you can just look at that if you like. Yeah. Oh, sorry. I should have left them, put them on the board. So, Chem Activity 8, page 168. For right now, 12 and 13. Yeah, these two. And then this reference, Chem Activity 12, 4, table 1, that's on the screen right there. So, number 12A, how do we not know if this is hydrogen or helium just from the fact that there is one peak? So why can we not tell? Yeah.
Don't they both have one peak?
Yeah, they both have one peak. They both have an electron in, or 2 for helium, but they're both in that first shell. So yeah, they would both have one peak. And what's question B is? Why it can't be lithium? Because lithium has 2 peaks, right? It has got an electron in the second shell. So we should see 2 peaks in that case, but we only see 1. So it's not lithium either. So this, we could figure out if we actually can look up these energies. So what is the ionization energy of hydrogen? What is the ionization energy of helium? So if we go back and look at these ionization energies, helium's 2.37 megajoules per mole. This is measured using the original ionization energy technique where you just bombard it with a high energy electron. And so 2.37, that matches, this must be helium then. So this is the photoelectron spectrum of helium. Alright, so this is not too hard so far, hopefully. Now, the peak height is going to be proportionally equivalent to the number of electrons. So with one peak alone, you can't tell anything. But if you've got two peaks in the diagram, and they're the same height, then that means they each have the same number of electrons in them. If one's twice as big as the other, then the other one has twice as many electrons as the other, okay? So that's what we mean by this. Hydrogen has one peak. Helium has one peak, which would be double the intensity. But without, both of them on the same graph, you can't compare them, right? So, what would lithium look like? Well, lithium would be two peaks. The shell 1 will have 2 electrons in it. Shell 2 is going to have 1 electron in it. So we should see one peak that's twice as tall as the other one. Now, the lowest peak energy is always going to be the ionization energy of that atom. Right? Because remember, the ionization energy is defined as the energy required to remove the easiest to remove electron, which is going to be the one with the lowest energy. So if you've got a diagram that has a bunch of peaks on it, the one furthest to the right, the lowest energy one, that represents the ionization energy of that atom, or that element. All right, so let's take a look at some more examples. So we're going to start with just questions 1 through 3 at Chem Activity 9. So page 170, let me write this down. 172 and 173, 1 through 3. And we'll spend about 7 minutes doing that. I'm going to scroll all the way back. There we go. Oop. There's a question about teams, so just think about what you would say at least. So ultimately, you're just going to do a quick sketch of what you think the spectrum looks like. Get the weird quirk that photoelectron spectroscopy, the x-axis goes the other way. Ionization energy goes up, going this way. It's just a weird quirk. many peaks are we going to see? I see people doing this. Yeah, 2. The relative size. One's going to be what? One's going to be what?
One will be around 4 times as big.
4 times as big. So you've got 2 electrons versus 8 electrons. The ratio is 4 to 1, right? So one's going to be 4 times as big. One's going to be whatever 1 big is, okay? So if we look at the energies, the first ionization energy of neon is 2.08 megajoules per mole. This is one of the peaks, so we can put it over here. Is the other peak going to be bigger or smaller? Higher or lower ionization energy?
Higher.
Higher. So this is the ionization energy. This is the first ionization energy. That's always the easiest to remove electrons. So any other energies that you need to remove electrons are always going to be higher, going to be harder to remove. So the other one will be over here somewhere. I don't know where exactly, but it'll be higher. Remember, and higher goes this way on this weird graph. What are the peaks going to look like? Well, so which one's going to be the 4 times high? Which one's going to be the 1 times high? So this one's going to be what? The 4 or the 1? The 4 times high, yeah. So you look at it, the valence electrons, those are the easiest to remove. That's the one where you have the most electrons. You've got the large number, 8 of them. So 8 to 2, 4 to 1. This one is going to be 4 times as high. So if I divide this into 4, 1, 2, 3, 4, like that, this one is only going to be 1 high. So that's what we should see if our shell model is correct. If this is a proper way to think about this atom, that's what we should see. Okay. Again, I'm giving it away a little bit, but this is actually what you see. This is neons simulated, but this is what we should see if we actually did a scan of neon. There's not 2 peaks, there's 3, right? So don't forget, this little hash mark thing just indicates as a change along the x-axis. It either means there's a giant gap that's missing, or the axis has changed. So instead of every 2, it's every something else. Here is just a big gap, okay? Otherwise it would be too long. So that's what we see. So let's answer some questions based on what we see. Numbers 4 and 5. We're going to have to revise our model, obviously. There we go. Represents. Don't forget, you need to come up with the same number of electrons neon has. Neon has 10 electrons. So somehow you need to assign, hey, this has got this many, this has got this many, and they add up to 10. And it should go along with their proportions. Okay, so hopefully you can see that it's 3 peaks. We just mentioned that already, not 2. The ratios are not quite right either. It's not 1 to 4. It's something else. These two are 1 to 1, right? You can see that they're the same height. If you actually physically measure this, so I'll say this right now. If we were really doing this properly, we wouldn't be doing peak height. We'd be doing area under the curve. But some of you haven't done calculus yet, so we're just going to do height. It's easier. So this is 8 inches long on the board. If I measure this one is approximately 24 inches long. That's a 3 to 1 ratio. 24 by 8 is 3. So 1 to 1 to 3, that adds up to 5. So if we double everything, 2 to 2 to 6, that adds up to 10. So that represents 2 electrons, 2 electrons, 6 electrons. All right. I think that's it for now. So given that information now, 2 to 2 to 6, let's refine our model. So something is wrong with our basic shell model. It's worked pretty well for the basic stuff that we've done so far, but suddenly it's not fulfilling its duty. It's too simple. We need to make it a little bit better. We need to refine it. And so I'm not going to go through all the steps as to why and all this, but scientists came up with the idea, well, these shells have subshells. The shells are broken down into smaller subshells. And I honestly don't remember the meaning behind the letters. I feel like it was a German thing, but I'm not sure. But we labeled these subshells the S, P, D, or F subshells. There's actually more than just 4. There's after F it keeps going with the letters of the alphabet, G, H, and stuff. But we don't need those. They're not really useful in what we're going to do. So these shells that we know of right now have subshells too. So for hydrogen, not only is the electron in the first shell, it's also in the subshell S of the first shell. So we would say that the electron is in the 1s subshell. That's, it's a combination of the shell number and the subshell identification. So 1s. That's where the first electron from hydrogen is. If we keep going, the second electron is in the 1s subshell as well. No different. You saw the photoelectron spectrum. When we looked at helium, there was 1 peak. And so the 2 electrons that helium had were both in the same subshell even. So again, 1s subshell. So when I get to lithium and beryllium, the 3rd and the 4th elements, they're going to go, and we already know that they go into the second shell, those next 2 electrons. But specifically now we're going to use the subshell notation. They're going to go in the 2s subshell. So again, the same S subshell, just in shell 2 now. That's all. So when you get to the 5th electron, this is when things get a little weird. The 5th electron is going to go into a new subshell called the P subshell. It's still in shell 2 though, but we're going to call it the 2p subshell. And that's actually what's happening with neon. So the shell 2 is split into 2 subshells. There's an S and a P subshell. And that's why we see those 2 peaks now. 3 total, but the shell 2 peak is split into 2. So we're going to use this kind of notation to identify what we call the electron configuration of an atom. An electron configuration is just a way to show the address of every electron in the atom. So 2 is the shell, P is the subshell, and the superscript notation indicates how many electrons are in that specific subshell. So this is saying there's 2 electrons in the 2p subshell. And so an electron configuration is usually written out horizontally. Sometimes you could write it on an energy diagram too. But lithiums would be 1s2, 2s1. What does that mean? There are 2 electrons in the 1s subshell, and then there is 1 electron in the 2s subshell. That's identifying every location of the electron of a lithium's electrons. So carbon, 1s2, 2s2, 2p2. Now, this electron configuration, here we go, actually starts to help explain why the ionization energy trend that we saw before wasn't perfect. So this is easy to understand. Helium dropping to lithium to a really low ionization energy is because we're putting the third electron in a new shell. That new shell is further away. And then we went up to beryllium. Why is it going up? Because we're adding electrons to the same shell, but the protons are going up. So more attraction. So yeah, the general trend is it's going up as you go across a period. But then we have this little tiny blip where the beryllium boron goes down. Briefly. Then it goes back up again. Why is that? Well, it's because of the subshell. So from beryllium to boron, we switch from adding to the 2s subshell to the 2p subshell. And if the ionization energy is suddenly lower, that must mean that the 2p subshell allows the electron to go a little bit further away from the nucleus than the 2s subshell. They have different energies. They have different potential energies depending on which shell they're in. So this is what's starting to explain some of these inconsistencies in the data that we saw earlier. It doesn't explain everything yet. Like, we haven't quite understood why nitrogen to oxygen goes down. We'll get to that. So let's kind of answer questions 6 and 7. Make sure that this makes sense on page 175. So spend a little time trying that. I guess they're right there. Wanted you to think about it for a minute or two, but 6, why are these right here? Why does this peak correspond to the shell 1 again? So the electrons in the shell 1. But why is it so high? Yeah, inner electrons, closer to the nucleus. They're not shielded by any other electrons. They're feeling the full, for neon, plus 10 protons, plus 10 positive charge at the nucleus. And so these electrons in the inner shell are just super tightly held up. And now, why are 2 of the 3 peaks assigned to the n is equal to 2 shell? So these are both shell 2, but now we have this new model. So they're both in shell 2, but they're in 2 different subshells. So this, which one is the S? Which one's the P?
P is 2.08.
Yeah, so this is the P subshell, and these correspond to electrons in the S subshell. Yeah.
Is it the strong nuclear force or gravity that's why it's so much different, more energy?
This right here?
Yeah.
It's electrostatic forces.
Ooh.
So there are 4, this is a physics thing. There's 4 forces, I think, in the universe. There's electrostatics, which is the attraction between positive and negative charge. That's what we're dealing with. There's gravity. Gravity is the weakest force, but it works over like super long distances. That's why it's so incredibly strong. And then the other 2 are stuff we'll never worry about unless you're a particle physicist. There's the strong nuclear force and the weak nuclear force, and those are the forces that hold together the nucleus, which is something we don't really worry about because it's beyond the scope of chemistry, at least this kind of chemistry.
Thank you.
All right. But yeah, positive and negative attraction, that's a big deal. It works. It's you know, what causes all the reactivity. All right, so these are some ionization energies determined from photoelectron spectroscopy for many different elements. And these are the electron configurations for some of those elements. You should be able to take a look at either one of them and kind of get one from, well, you should be able to look at this kind of data and try to get this kind of information from it. So let's look at Chem Activity 10, questions 1 through 6. This is basically focusing not on the photoelectron spectroscopy, although we're using that data. We're going to actually look at the electron configuration portion of it. Okay? So how do we address where the different electrons are? Is there a pattern to it? Things like that. This might be like syncing up with high school chemistry. If you were attending high school chemistry, they kind of go right into this without explaining where it comes from. Honestly, these questions are just getting comfortable with this data, getting comfortable with looking at configurations like this. So I'm seeing some people doing the right thing. I'm seeing some people doing partially the right thing, which is still fine. So first, let's look at question 1. Using just the data that was given, how do I find the N for the valence shell? So the valence shell is the outermost shell. I can look at well, I can't do the electron configuration for nitrogen, but if I look at the photoelectron spectrum energy for nitrogen, it's got an energy for 1s, an energy for 2s, and an energy for 2p. That means there's electrons all the way out to the 2p, or the energy shell 2. So that's its outermost shell, is shell 2. For argon, the outermost shell, we have electrons all the way up until 3s and 3p, so shell 3. Ionization energy 1, all right? Remember what an ionization energy is. It's the cost required, the energy required to remove the easiest to remove electron. So it's always going to be the lowest number for that element. So for argon, this one is the lowest ionization energy for any of its electrons. That's going to be the ionization energy for argon. It costs at least this much energy to remove an electron. That's it, 1.52. For nitrogen, 1.40. So it's always the smallest one. So again, this technique is super powerful because it gives us all the rest of the electrons as well. That's why it's better than just the plain old ionization energy data. So next, they're asking, well, I guess there's some thought questions, but the major one next is draw a photoelectron spectrum for argon. And I think people were drawing the peaks in the right spot. So there's one at 1.52. There's one nearby at 2.82. And then after that is a big gap, which is not represented on my scale. So I'm just going to put a little hash mark there. And then there's another one way over at 24.1. And then there's another one at 31.5. And then there's a huge gap, because now we're getting into the hundreds. And there's another one at 309. But the other thing you have to take into account are the heights of the peaks. The height of the peak represents the number of electrons. And if you're not sure, you can look at the electron configuration. That'll tell you how many electrons are in each section. So there's going to be 6 electrons in the 3p subshell. And if you didn't notice the column headers, it told you this was the 3p section. So if I mark off in threes, 1, 2, 3, that's fine because my ratios, 2 to 2 to 6 to 2 to 6, is the same as 1 to 1 to 3 to 1 to 3. So in terms of how high the 3p peak is going to be, it's going to go up to my 3. I can draw this vertically. The 3s is going to go up to 1. And then my 2s is next, goes up to 3. I'm going to get right in front of it. 1, and then finally 1. That's what you should see, is the right heights as for the peaks too. Okay? So far so good, hopefully. So really, what is the relationship between the data in tables 1 and 2? You know, it's basically table 1 gives you the energies of those shells, of the subshells, and table 2 gives you the number of electrons in those subshells. So they both represent some information about the subshell, okay? What else? Is it possible to deduce the electron configuration from an atom from its photoelectron spectrum? What do you think? I see head shaking. Yes, yeah, you can. So just looking at this, I can go backwards, okay? The highest energy peak is always going to be from shell 1. And shell 1 has an S subshell, and that's it. So that's the 1s. Next comes the 2s. Next comes the 2p. Then comes the 3s. Then comes the 3p. Now, this is not going to be easy until I teach you or show you a better technique for memorizing what's next. But that's the identification of these subshells. And then the heights of the peaks will tell you how many electrons there are. Now, you might say, oh, how do we know it's 1 versus 2, double everything? You're going to learn that as well. The S subshell can hold a max of 2 electrons, and so this thing is full. The S subshell holds a max of 2. The P subshell holds a max of 6. How do we know that? Why does that make sense? Well, we know that the shell 2 holds a max of 8. Right? So shell 1 holds 2, shell 2 holds 8, shell 3 holds 8. Well, there's shell 1, it's got 2. It's the subshell, but it's still got 2. These two subshells combined make 8. These two combined make 8. Although the last one, it's a coincidence, it's full, but because it's neon, or argon, excuse me. Okay, so you can definitely look at a photoelectron spectrum and deduce an electron configuration. And deduce what atom you're looking at. I know that's argon because the shell, the valence shell is full. It's got 8 electrons in it. It has to be argon. Kind of. What about ions and stuff? Well, we'll get to that too, but if it was neutral, I know for sure. So, what do you guys think we're looking at right here? Table at the bottom that might help. Okay. I'll put a quick guess in. If not, you don't have to. I'm going to stop it. And so before I show, well, let's actually see what people voted. Most people said A. So yeah, if you go 1S, 2S, 2P, 3S, 3P, what comes after 3P? Well, there's this 3D in there. But this only shows up as long as there's a 4S also, okay? So there's only one more peak, so it has to be the 4S. Now, let's look at the heights. This represents 2 electrons, 2 electrons, 6 electrons, 2 electrons, 6 electrons. This one is half as tall as that one. So that only represents 1 electron. So the 4S has 1 electron in it. That has to be potassium. Calcium has a 2nd electron in it. It's got 2 electrons in shell 4. But potassium only has 1 electron in shell 4. So this is definitely potassium. Alright, so you'll have to understand how to come up with an electron configuration and then count electrons based on what you see on the photoelectron spectrum. Now, this whole, 1S, 2S, 2P, how do you know this? How do you memorize this? When does the 3D come in? How do you know any of this stuff? There is a trick to remembering the order of these subshells. And this is I learned this, I think, first. And I remember it very well, so some of you might like this pattern. So you start off by making a grid, 1S, so 1, 2, 3, 4, 5, 6, 7 all the way down. And then you add the subshell, 1 extra subshell each row. So 1S by itself, 2S, and then 2P, then 3S, then 3P, then 3D, the next one, then 4S, then 4P, then 4D, then 4F. We don't add any more subshells because they don't really exist very easily beyond F, but that's what you do. And then once you've drawn your grid out, you do diagonal lines starting from the top right going to the bottom left. It seems overly complicated, but I remember it, so it works. So 1S comes first, then 2S, then 2P, then 3S, then 3P, then 4S, then after 4S, 3D, which seems weird because it's 3, but that's come next. Then 4P, then 5S, then 4D, then 5P, then 6S, then 4F, then 5D, and 6P. So this is one way to do it. And when you stack them all up in terms of the energies, this is kind of what you see. So 1S is the lowest energy, then 2S, then 2P, then 3S, and it keeps going up. Now remember that as your energy levels get higher and higher, the spacings get smaller. So that still happens with the subshell model. It's just we have lots more energy levels now. Now, I still remember this, but I like a different method better. And I like the periodic table method. So what you're seeing here is the periodic table. If you cut the periodic table right here and stuck the lanthanides and actinides right there where they belong, kind of in sequence, right after barium. Now, you don't have to do that, but that's kind of how you should visualize in your head. And the periodic table is broken up into subshell blocks. It's kind of naturally done that way. So imagine the helium over next to hydrogen. That's the only other thing you have to do. And the two groups, the two columns on the left, that's the S block. And then this giant area here, minus the helium, is the P block. The transition metals inside here is the D block, and this is the F block. And then to do an electron configuration, you kind of look at an element. So for instance, sulfur, just pick one. And then you follow the periodic table from 1 all the way to sulfur, and the row and the block will tell you what's the next subshell. So 1S is first, but there's nothing else in that row, so just 1S. And then the next row, 2. 2S is next, then 2P. Sulfur is right here, by the way. After 2P comes 3S, and after 3S comes 3P, and I would count 1, 2, 3, 4 to sulfur. So we put 4 electrons in the 3P block. Everything else is full. That's how I remember it. When you get to the D block, transition metals, you have to remember to subtract 1 from the shell number. It's a little annoying, but that's one of the things you have to do when you do this method. So for instance, if I was doing the electron configuration of vanadium, 1s, 2s, 2p, 3s, 3p. So after argon comes potassium. That's the row 4, S block, 4s. Now we get to the D block, but when you get to the D block, remember to go down 1 shell. So it's not 4D, it's 3D. It's 1 minus the period number for the D block. So after 4S, 3D, and we have 1, 2, 3. So we put 3 electrons in the 3D. If I were to keep going, say I did arsenic, okay? 4S, 3D, back to 4P. When you do lanthanides and actinides, it's a similar idea to what happens with the transition metals, but we go down 2. So if I were to do europium, all right, 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, and then this is where we drop down to here. Because right after barium, we get to the lanthanides. So 6, we drop down 2 to 4, F, and then it's, what is it? 1, 2, 3, 4, 5, 6, 7. 4F7. Every periodic table is a little different. This one, for some reason, has lanthanum and actinium here instead of here. But this is part of the F block, these two right here. So it's 1, 2, 3, 4, 5, 6, 7. That's how I do it. I think that's the easiest method because you're always going to have the periodic table handy. And that's how you know what the order of subshells is. And there you go. There it is as a cheat sheet if you need it. But while you're, you need to learn how to do it without the cheat sheet. You need to look at a periodic table and be able to do it. All right. Now, how many electrons is each subshell capable of holding? The periodic table gives it away. How many elements are in each row in the S block? 2. So S subshells can hold 2 electrons. That's it. How many elements are in the P block in a row? 6. Right? 1, 2, 3, 4, 5, 6. So there are 6 electrons allowed in the P subshell. Excuse me. D subshells. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons allowed in the D subshell. F subshells. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Or if you want to count this one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That would technically be up there. But 14 for the F block. Okay? So, the number of elements in each section tells you how many electrons each subshell can hold. So yeah, I like this method. Here's a normal periodic table broken up into blocks. So again, just remember the helium technically is over here. And then you have to subtract 1 from the D block and 2 from the F block for the shell number. So, this comes with questions like this. What is the electron configuration for nickel? To make these easier, just make sure everything is the same up to a certain point. So, up to about here, everything's the same. So you're just looking at the last 2 parts. Okay. So, I'm going to stop it. If I didn't want to guess, it's okay. Stop it there. Those 5 people, a little bit varied answers, but most people think C. Most is a very relative word. So here's how I would do it. I would, they're all the same up to that 4s. So let's start at row 4 with nickel. And so I would say nickel is going to have, the last part of it's going to be 4s with 2 electrons in it, full. And then over here, 1, 2, 3, 4, 5, 6, 7, 8, 3d with 8 electrons in it. So it's got to be this one, 4s2, 3d8. And you can always double check your answer a little bit. You can find the total number of electrons. So nickel should have 28 electrons, same as its atomic number. These should add up, the superscript parts should add up to 28, which is a lot to add up, but that's one way to check. Okay. Now, they do get tedious to write. It's a lot to write. So we've got shortcuts for writing it. So we've got something called the noble gas notation. Before I get to that, I just want to make sure that the transition between what we've covered before and what we've covered now is clear. We had a shell model before, and the shell model was easy to draw out. I mean, it was a very limited number of shells. It's, when you got to 4 shells, it was a lot of electrons to draw. But now that we have the subshell model, we could draw it out just like the subshell, but that would be a lot. It would be really busy looking. And so this stuff, this kind of shorthand notation, is a lot easier to read. So that's all we're doing, is we're just expanding our model we're not having a picture anymore, but it's the same idea, okay? But now even this is getting a little bit too much to write. Not really, but it is. We can say that. It turns out that the first part of sodium's electron configuration looks exactly like neon's. So neon's electron configuration is 1s2, 2s2, 2p6. Notice they're the same. And so you can do a shorthand notation. You can say, well, sodium's electron configuration looks like neon. That's what the bracket neon means. And then at 3s1 is the rest of it. So noble gas notation is the way to go in general. It makes things so much easier. So calcium is argon, looks like argon with 4s2. So how would you do this very easily? Calcium is on the periodic table right there, number 20. You go backwards. What's the noble gas that comes right before calcium? It's argon. So I put argon in brackets, and then the next is the 4s2, 1, 2. That's it. 2 elements over to get to calcium. Calcium is still in the s block, so no other subshells, just the 4s subshell with 2 electrons in it. So these are also known as condensed electron configurations. So you'll see both, the full and the condensed versions. Okay. So if we had to do that for magnesium and bromine, bromine and magnesium's full electron configuration would look like that. 1s2, 2s2, 2p6, so forth. If you do the noble gas shortcut, the condensed version, they look a little easier to read, shorter. Bromine looks like argon at first, and then it continues on 4s2, 3d10, 4p5. Magnesium looks like neon, and then it continues on 3s2. Okay. So, what about ions? We were looking at neutral atoms. Again, ions you form when you take away electrons or add electrons to the valence shell. This is where this kind of starts making sense, hopefully. Most cations that form, and remember only really metals make cations, those metals make cations that tend to have electron configurations that look like the noble gas that's right previous to it. Anions tend to go the other way. So nonmetals like to gain electrons. They like to make anions. And their anion electron configurations look exactly like the noble gas that's in front of it. So calcium 2+. Right? Regular calcium is calcium with 4s2. And if I lose 2 electrons, those 2 electrons in the 4s2 are gone. And now that's what the electron configuration is. It is exactly the same as argons. Sulfide, which is s2 minus. So sulfur normally is this 3p4, right? It's the 4th element over in the 3p block. If I add 2 electrons, it becomes 3p6. That's the same as argon. What's the word we use when they look like that? Another word we just learned. Isoelectronic. These are isoelectronic species. They have the same number of electrons. And they happen to have the same electron configuration too. So calcium 2+, sulfur 2-, and argon are isoelectronic. Okay. What would be the electron configuration for boron if I use the condensed version? It's not much of a condensed version, but technically that's the condensed version. Boron is number 5. Everybody's got a part. It's okay. All right. So, sorry, so you'd be right, it's D. So again, to do the condensed version, take the element you're looking at, go backwards until you get to the first noble gas. So boron going backwards, helium is the first noble gas. So I'm going to put helium in brackets, and then after helium is row 2, and that's the S block, so 2s, how many electrons? 1, 2. And then next is the 2p block, 1 electron, it's the first element in the p block, so 2p1. 2s2, 2p1. I keep saying it's not much of a condensed notation, it's not much of a shortcut, because what is helium's electron configuration?
2s2 or 1s2.
1s2, yeah. So you're not replacing much. But that is technically what the condensed configuration would look like.
If you're typing it out, it's actually one more character.
Yeah. Well, but you're not doing a superscript. So that's usually hard to type. Harder to type. Anyway. Okay, so what about an ion? Rubidium plus. What's the electron configuration for rubidium plus? Stop it there. People are saying, ooh, split between C and D. So rubidium, the original neutral atom, is D, but rubidium plus is C. So rubidium, yeah, you would do the noble gas right before it, it's krypton, and then rubidium, the neutral atom, would have an electron in 5s1. But, so that's neutral rubidium. Rubidium plus means you've lost 1 electron. That's the electron that's lost, so that's empty. We don't write empty subshells, and so we're just left with krypton, the inside of the krypton. I'll say this. I will accept this as an answer as long as it's clear that you're answering what is the electron configuration. But a lot of professors won't. They don't want you to write just noble gas with brackets, because I'll tell you why. If you were to write krypton with brackets anywhere else, I would think you're talking about a concentration of krypton, not an electron configuration. So just be clear. A better answer would be argon bracket 4s2 3d10 4p6, right? But this is fine. This is fine for me, okay? It just looks weird sometimes because by itself it doesn't look like an electron configuration. All right, so now that we've finally got the last piece of the puzzle for our electron, like how to talk about electrons in an atom. This new shell model fits all the data we've seen so far. Let's kind of complicate things even further. So we know that these energy levels exist, right? All their energy data shows that they do exist. There we go. We've got 2s and 2p. What's incorrect is kind of how we think about it, right? So we've been using this kind of orbiting around the nucleus model. With the shell model at least, we have electrons orbiting. That's not the right way to think about it. It turns out that that these electrons are in many, many different places at once. They can be varying distances from the nucleus. They don't have to be a certain distance all at the same time. So it's more complicated. And this is where we get into quantum mechanics. We have to apply this concept. And so here's what's weird. So far, we've only talked about quantum mechanics in terms of light, I guess. We've applied, so in the old days we used to think of light as a wave. And then we have this new way of thinking, oh, light is both a wave and a particle. Right? We think of light as a photon. Can we do the same thing with an electron? An electron is a particle. but could we think of it as a wave too? Which is weird because we know the electron has mass, it's a thing, it's matter. But that's what we have to do. We have to think of the electron as both a particle and a wave. And this is where quantum mechanics comes in and makes it hard to visualize the electron. So actually I want to show you this, and I think that's all I want to do right now. Oh no. Alright, hold on a second. I know it exists. What is it called? Dr. Quantum. They get bootleg all the time. There we go. Hopefully this works.
And here we are, the granddaddy of all quantum weirdness, the infamous double-slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. And it goes through just one and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange netherworld of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
So, yeah, question.
I've heard of an electron field. Is it?
I mean, yeah, I think probably when describing the electron that way, you're describing it in terms of a wave instead. But that's what we're going to get into. We're going to get into this idea that when you're at the tiny, tiny particle level that we're looking at, matter stops behaving the way we expect it to, and it starts having properties of both wave and matter now. So we're gonna, you saw that, it made the interference pattern just like light did. And so what we're gonna have to figure out, learn is that these orbits, that electrons don't do that. We can't actually say an electron is here with any certainty. It's basically now gonna be a wave. Like, so how do you say where a light wave is? You can't, it's like all over. Like a wave is a long continuous thing. You don't say the wave is just here. You say it's you know, where does the wave start? Where does it end? If it's a wave. So we're gonna have to talk about the electron the same way. This is where probability comes in. When we talk about where an electron is, we can't say it's here, but we can say there is a 90% chance of finding the electron in this region, kind of thing. So we'll have to change the way we talk about electrons, change the way we think about them, and then some of these new observations we're going to look at will start to make sense. So we're going to get to orbitals. So the concept behind an orbital. I mean, it's based on the word orbit, but it's not at all the same thing. An orbital is a calculated region of space where you're most likely to find a certain kind of electron. So we're not going to get into too much to the equations, all that stuff, because that's beyond what we can cover in this course. It's more of a physics thing, or physics, chemistry, quantum stuff. But we'll kind of look at the results of that. So we'll get to that. But yeah, so I just wanted to show you that experiment because it's kind of mind-blowing. It's like, I didn't know matter could behave like that. Yeah, so there's a famous equation called the de Broglie equation. And it's a way to calculate a wavelength of matter. So you can take something that has mass and calculate a wavelength for it, which is weird, but you can do it, and it works. It's verifiable, I should say. Yeah. Anyway, that's it for today. We'll stop for now. We'll talk about quantum mechanics next week. I mean, we've already started doing it. That was what the beginning of Connectivity 7 and all that was about. So. Yep.
Where should I meet you?
Oh, so near the office that's right around the corner, the big double doors over there. There. Yep. So the double doors are right there, over on the side. Just knock hard on it, and I should be there. Yeah.
Awesome. Thank you so much.
I can't unlock them permanently, though, so they have to stay locked. So.
Okay.
I should say, even though we can't physically describe the quantum world, we can describe it mathematically very well. So math is all we have left. Yeah. Take it easy.